Welcome back to What's New in Data. I'm your host, John Couttet. Today I'm joined by Marc Brooker, VP and Distinguished Engineer for Databases at AWS. Marc has been at the forefront of building some of AWS's most critical infrastructure, and today he's focused on their distributed SQL database services. In this episode, we'll dive into the architecture behind AWS's distributed SQL offerings, namely DSQL. And we'll also talk about the future of cloud databases and lessons from building resilient, high-performance systems. Let's get right into it. Marc, how are you doing today?
Yeah, I'm doing great. Super excited to be talking about DSQL and databases more generally. Always a fun thing to talk about.
Yeah, absolutely. I know the listeners are excited about this one. You've written a lot of awesome technical blogs on this topic, and we're going to dive into some of what you discussed. But first, Marc, just tell the listeners about yourself.
Yeah, so I work at AWS, and I've been at AWS for 16 years, engineering the whole time. I've done a little bit of management on and off, but I've been a primarily individual contributor, throughout that career, and I have worked on a whole lot of different services at AWS. Most recently, in our databases and AI businesses, but storage before that. I joined the team that built AWS Lambda, soon after the preview launch of that product. I worked on the EC2 team, and in the early days when, folks were still saying, why would I buy my IT infrastructure from a bookstore? And so it's been a super fun journey of just seeing the cloud grow and this whole industry grow around it. Before that, I joined AWS almost completely from a completely different background. I was at grad school. I was building radar systems, doing electrical engineering, and kind of distributed background, but not not computing, not distributed computing, not the cloud at all. And so it was a really fun kind of career pivot back in '08, and one that I think in retrospect I've been pretty happy with.
Yeah, excellent. And definitely, so much value has been delivered with services like EC2 and cloud computing in general. And, it's changed the entire landscape for how you build and scale applications, whether you're a mom and pop small business, or if you're one of the world's largest and most sophisticated enterprises and tech companies as well. So very cool to be chatting with you about what you've been working on recently, which is DSQL. So I wanted to ask you, who is DSQL designed for, and what key challenges were you aiming to solve for your users with this service?
Yeah, so there are kind of two things there. It's almost kind of two products, in one. One of them is we have this set of customers who have been building on serverless. They've been building on containers, and what they've noticed is that, they've continued to love the relational data model, love SQL for all of the reasons for that, want transactions and all of that good stuff. But what they've noticed about most relational databases is they require a lot more operational care. They require a lot more scaling care and attention to scaling. They don't have the kind of scale and dynamism that folks expect from containers and serverless. Often they have things like connection limits, which get in the way. And so one set of customers we were really trying to help out with DSQL is people building on that kind of modern cloud native computer architecture, to give a fully relational database experience, to give SQL, to give transactions, to give ACID, and all of that good stuff, to folks building on that kind of infrastructure in a way that can keep up on scale, equals on simplified operations and so on. And then almost at the other, I wouldn't say the other end of the database market, but in a different part of the overall, picture of transactional databases, there's a set of folks building extremely highly available applications, building, critical applications, often applications that are, critical to their countries or the world's economic or transportation infrastructure. And these are folks who are building, um, often have internal requirements or regulatory requirements to run in multiple regions, to have geographic diversity, to have the ability to move workloads away from entire regions. And one of the patterns that folks love, and for good reason, is active-active, right? Like they want to build in a way that their application is running concurrently in region A and region B. They want to have, again, SQL, ACID, the relational data model, and all of that good stuff. They want strong consistency. They want transactions. And DSQL is also being built for that set of folks with multi-region active-active, high availability and durability across 3 AWS regions, the ability to remain available even when an entire region fails, no data loss or consistency loss on failure. And so, two fairly different use cases. There's some intersection between them, but not an awful lot. But those are the two big things that we were trying to go after with this new Aurora flavor, Aurora DSQL.
Yeah, and DSQL is serverless, and that's one of the big advantages of it, and it's distributed. But you don't lose. It seems like based on how you designed it, you don't lose the availability and consistency of having this massive dedicated. Maybe it's a clustered database, right? So when I traditionally worked in building cloud applications, it seems like, if you wanted to quickly build a demo or something, sure, use serverless. But once you knew what your throughput and requirements would be, provision the infrastructure, plan your run books for failover, and you're probably going to need some dedicated infrastructure for that and significant planning just to maintain the infrastructure for an application in addition to the databases and the software stack. But what you're saying is you get all the advantages of serverless and the advantages of a clustered, highly available, distributed database.
Yeah, that's been our goal. And as we get into the technical details there, we can talk about some of the trade-offs. But one of the things that we do at Amazon is, when we're building a big product like this, and always, but especially when we're building a big new initiative like this, is to spend a lot of time talking to customers and prospective customers about their needs. And one of the words that I heard a lot having those conversations was regret, right? Like, hey, I want to start with something that's really easy to get going, that's low risk, that I can build a meaningful application with a small engineering team, but I don't want to regret that choice as I grow, as I'm successful, right? Like as my business or this internal product or whatever moves up and gets bigger and gets more critical. And so that's really been our kind of core focus here, is saying, this is going to be a great choice at small scale. It's going to be easy to get going. It's going to be easy to build that sort of V1 of your application. But then you're not going to regret that choice over time. It's going to grow with you. It's going to, meet your most critical operational requirements. It's going to grow with you on scale, on availability, on durability, on enterprise integrations and all of those other pieces. And so that's a big part of that vision, because we don't, it's great to have serverless products that make it easy to get going with something, easy to build a V1 of something. That's valuable in itself, but it's even better if you can build things that way, and then you can, slowly evolve them and adapt them into being, huge and meaningful businesses. Because the worst day in any application team's world, or nearly the worst day, is when they have to go to the business and say, well, for the next year, you have to turn customers away while we do a big re-architecture or while we replace our data store. I think nobody wants to have that conversation. But too many people do have it. I've had that conversation in my career, and I hope to never have it again. And so that's part of our, that's been a big part of the kind of drive behind this vision, is that, folks can pick DSQL and then it will grow with them, grow with their requirements, to businesses of literally any size.
Absolutely. And that's a great point that, yes, teams may build that V1 version of their product on serverless or however they design it, but it may not scale once they've become successful and have tens and thousands of customers. And like you said, migrations can take years. Like infrastructure migrations can certainly take years, and a lot of additional planning and costs for zero downtime in those scenarios. So I do want to get into some of you mentioned trade-offs, but
Yeah.
specifically you talk about active and multi-region architecture, and I'm sure even cross, availability zone. I'm sure that's all there. Can you elaborate on how you balance the trade-offs between availability and consistency and latency in this design?
Yeah. Yeah. So, I think probably the first law of physics there is a consistency versus latency one. And so at the moment that you say to the database, commit, right? Like, I want you to make this transaction durable for me. The database can do one of two things. It can do, it can make that durable locally, but in the multi-region setting, it can either send the data over and then while it's in flight, say it's committed, or it can send the data over, wait for it to have been sent, wait to get acknowledgement, know that it's durable on the other side, and then return that commit. And, so the difference between those can be, no impact, no RTTs of communication versus having to wait for at least one round trip between a pair of regions. And so that's trade-off number one. And so what we've done with DSQL in its current guise, and we might provide more control over this later as the product, grows. But we have chosen synchronous, right? Like when you call commit, in that 3-region setup, we're going to make sure it is durable in storage in 2 of those 3 regions before we return, that commit to you. And that does increase commit time latency, not write time latency, crucially, but commit time latency. But it does ensure that you can lose an entire region without losing any data. As an upshot of doing that durability work, almost secondary to that, is now that we've moved the data over, we can, with very little additional latency cost, provide strong consistency. And so that's the other part of it, is to say, can I assume that if I have done a commit in region A and I immediately go to region B, I can see the effects of that commit immediately? And again, if you do this replication asynchronously, the answer to that would be no, right? That replication might still be in flight and might still be, being applied. But what we've chosen is consistency. And so that's related to the synchronization.
And when you say synchronous versus asynchronous, you mean when you are ensuring the durability, sending the commit out to the other nodes or whatever pieces of the stack exist, are you sort of holding the world in a sense and kind of pausing the database at that point before you've ensured that it's been acknowledged by the other nodes?
Yeah, so that's a great question. The answer literally is no, you don't need to pause the whole database, but you do need to potentially wait on other writes to the same keys. And so if I have a million rows in my database and I'm update row A and row B, and those are in separate transactions, they don't have to wait on each other. They can be fully parallelized. However, if I update row A in region 1 and I update row A in region 2, there needs to be some handshake. And that handshake is there mostly to ensure the other important property here that we haven't spoken about yet, which is isolation, right? This transaction isolation. And providing the transactionality guarantees in this multi-region active-active setup. And so you certainly don't want to be in a world where you're slowing down an entire data set. And so you don't have to do that from a kind of law of physics perspective. But once you have a single key which is being accessed from multiple places at the same time, there does need to be some, at least 1.5, I think is the physical limit, rounds of communication to ensure isolation and to ensure that consistency. I wanted to jump quickly back to availability because you asked about that. And so I think what's important in our model is this is a 3-region model. We have 2 primary regions that are witness. And if one of those regions fails or becomes partitioned off, and not communicatable, the database is not available in that region, but will continue to be available and strongly consistent in the two remaining regions. That's kind of the majority side of a partition. And the alternative to that would be to be available on both sides, but to do that, you would have to give up consistency, and you would have to, once that partition healed, you would need to be able to post-merge data. And so if you look at another product like DynamoDB Global Tables, that is the decision that we made there, is to be available on both sides and then post-merge. That's got great availability properties, and what we've decided for DSQL is to be available only on the majority side. And then when that partition heals, you can copy the data over, repair the cluster fully deterministically without giving up any of the asset properties, and get back to 3 running regions.
Yeah, absolutely incredible. And the other thing that's impressive and notable about this is you fully leaned into the AWS software stack to deliver this solution. So one example which you wrote about is using EC2's precision time infrastructure for synchronized clocks. And people who are familiar with distributed systems engineering know the significance of having clock synchronization and even the precision of the operating system, how it perceives time and things along those lines, making sure that's all in sync. So can you explain how you use EC2 and AWS's clock synchronization support?
Yeah, and so as your listeners might know, we've been rolling out. We rolled out time sync service to EC2 a few years ago, and we've been rolling out a big improvement on that over the last year or so to bring time synchronization globally to EC2 instances down to tens of microseconds. And so that's available, to regular EC2 instances, and over time will be available to all EC2 instances in all regions. And so taking advantage of that, one of the things that we did that we use that for is ensuring that reads are strongly consistent without needing any coordination between regions or even within a region for reads. And so we might touch on this in more detail later, but the core idea there is when you send a read in a transaction, and so that could be a select, it could be an update, right? Because an update in SQL is a read modify write. It could be an insert, because inserts on unique keys also require some amount of reading, or any combination of those things. At the time your transaction starts, we look at that local clock from the EC2 time sync service. We read its current value, and then throughout the rest of the transaction, every time the query processor, which is running that SQL, goes to storage, it goes to storage and says, give me this data I'm looking for as of that time. We call it T start. And by saying as of T start, what we can do, when combined with the fact that storage keeps track of multiple versions of data and can answer that as of question with perfect accuracy, what we can do is give that transaction a fully consistent snapshot across the entire data set in the database, even if, with no locking, with no latches, no locks. And even if we don't know, and you don't in SQL in general, you don't know which keys are going to be accessed. And so, this is a big partition database, it's a big partition feature set, big partition data set. And so you'll go to partition C and say, give me the row for cat. As of this time, you'll get that back. You do some thinking, maybe you run some of your application code, you go back to the client, and actually, I also need the row D for dog. Go to D, say, give me the row dog as of that T start. And what you'll be sure of is that the row C for cat and the row D for dog that you pulled up will be at a consistent point in time in the database, right? One won't be a transaction ahead or a transaction behind or whatever the case may be. And that's really great for isolation. But because of the use of time and the use of multi-versioning at the storage layer, that doesn't require any coordination between shards, even between replicas in a shard. It doesn't require us to have a single primary replica for a shard. It doesn't require cross-region or cross-AZ coordination. And so there, in an availability zone, between one pair of machines, we can do those reads to another shard or partition, pull that data together, and still have that strong read isolation, snapshot read isolation, which is very cool. It's a very cool property. And then doing that with a clock that's well synchronized to physical time allows us to make sure those responses are also ordered in physical time, which provides this additional property of linearizability or strong consistency, where you can be sure that you're going to read your most recent writes, and you're going to see all of the effects as of a real time in the database.
And is most of this happening? There's an underlying database engine behind this, but is this synchronization happening in kind of a software layer of abstraction that's head of the database or separate from the database itself?
Yeah, it's kind of separate. So, our literal SQL engine, the thing that is running SQL, that is, running those transactions, is doing query planning and optimization and so on, is Postgres. And we can talk about how we made that choice. I think it was a really great choice. I'm a huge Postgres fan. But then below that, when Postgres says, "Hey, I need some data to return to the client or to process this query," we have that's where our custom implementation starts. And so Postgres will say, "I need this row as of this time," and that's where we'll have an implementation that goes off and finds the right partition or right shard. It figures out, which of the SQL operations it can push down to be processed down at storage, which is a big latency win. It finds a healthy replica. It finds a nearby replica. Maybe it talks to the control plane to say, "Hey, you need some more replicas of this data." It does that whole thing, and then it gets back to Postgres and says, "Here are the rows that you need to process this transaction." And then Postgres will do things like the join logic and all of those kinds of things that relational engines are just really great at.
Absolutely, because what you're describing sounds like something beyond any database engine itself has offered in terms of having there's been databases that, clearly can scale in the cloud, and there have been, scalable cloud databases offered and mostly using, sharding and partitioning. And then there's cluster databases as well. But to do this with a serverless offering is truly unique. And, it's the first that I've seen of it at this level of control around, uh, you know, disaggregation of compute and storage, and strong consistency and isolation, and these very sophisticated multi-region setups with high availability. So that's why I was asking. I don't think there's a database engine that would just you could pull some knobs and set something up like this yourself.
Yeah, I'm not aware of one, although there are some really interesting distributed SQL engines in the world and some really cool technology there. One of the choices that we made as we designed DSQL was to try and disaggregate the database into multiple concerns. And so, we tried to separate out the distributed system concerns from the core relational concerns. Now, there's some leakage across that boundary. The relational engine can't be entirely oblivious to the fact it's running in a distributed context, because it has to know some of that to make good query plans and to do good query execution. But it doesn't have to know anything about how many replicas there are. Are there replicas? Where are they situated? How do I find them? Have they failed? And so by taking all of those, hard distributed system concerns and separating them out into a separate component from the database engine, it's allowed us to keep that database engine, quite simple, quite stock, and that's useful operationally. But it's also organizationally allowed us to have, the folks working on that part of the system be deep database experts rather than, deep distributed systems experts. And that's a really big win, just organizationally and as an engineering team, is to be able to, have a level of specialization like that. And and so what we've tried to do is make that Postgres layer as um, unconcerned, I wouldn't say oblivious, but unconcerned with the realities of being in a distributed system as we can.
Absolutely. And I'd love to hear about, how you approach offering strong consistency and isolation in multi-region setups. So that's also very interesting and unique. And the use of, you wrote about this, but the use of optimistic concurrency control and multi-version concurrency control as well, and how does that contribute?
Yeah, so that's a really deep
Yeah,
topic.
yes.
But yeah, let me get into some of that. I think you know multi-version concurrency control is the first part of that, and that is this idea that on the storage node, we have multiple versions of each piece of data, versions spanning over a time window. And so that allows the query processor to go and ask for data as of a particular time. And so that's a sort of data structure at the storage layer with multiple pieces of data in. And the benefit of that, as sort of touching on what I said earlier, is that the query processor can form a consistent snapshot of the data in the database without having to do any coordination between nodes with other query processors. Doesn't even have to be aware that other query processors exist. It doesn't have to go to a leader for a shard. And so that multi-version concurrency control step on the read side pretty much eliminates the need for distributed coordination in the system. And then we get to the write side, and that's where things get really interesting. And so I would sort of break that down according to the ACID properties. And so as you commit a transaction, you need to do two things. One of them is isolation. And that simply means, given a particular isolation level, can this transaction commit while keeping a certain set of rules about the transactions that it ran concurrently with? And at the isolation level that we currently support, which is called strong snapshot isolation, the rule is fairly simple. A transaction can commit as long as, given the set of keys that it's updating, the keys that it's writing, nobody else has written those keys between when that transaction started and when it's trying to commit. And so it does the step where we have another separate piece of the database called the adjudicator, where it looks at the set of rows that it wants to commit, and it goes to the adjudicator and says, my transaction start time was 5. It's now time 7. I want to commit keys A, B, and C. Are there new versions of these keys in the database since I read those? And the adjudicator can say one of two things. It can say, no, there are no new versions. That's fine. You can go ahead. Or, yeah, there are new versions of these keys. You need to abort this transaction. And that is all the coordination that is required to meet this strong snapshot isolation level. The next step is the most important one, and that is atomicity and durability, right? This is where a commit actually becomes a change to the database. And so what we do once we've passed those isolation checks is we package up the set of changes to the database. We choose, based on the isolation checks, a version number for it, a point in time for that transaction to take effect, and we write it to a service called journal. This is an internal component we've been building at AWS. We use, for over a decade, we use it in all kinds of places. We use it in S3, we use it in DynamoDB, we use it in Lambda, we use it in Kinesis. And what journal provides to the database is two things. It provides durability, In the single region mode, that means on storage across multiple availability zones. And in the multi-region mode, it means on storage across multiple regions. And it provides atomicity, this kind of core database property of I'm either going to accept this whole transaction or I'm going to accept none of it. And so once we've handed that off to journal, then we know that we've passed our isolation checks, that commit is atomic, and that commit is durable, and we can go back to the client and say, your commit has committed. Congratulations. Now, then at that point, in parallel, what we're going to do is apply that commit, apply that change to the relevant storage nodes. And so that's, and then sort of looping back to your question about optimistic concurrency control, that check with the adjudicator is optimistic concurrency control, right? We have allowed the transaction to run in its entirety, to do a bunch of reads, to spool up a bunch of writes, to communicate with the client. We have not coordinated with other transactions up until this point. And then at that commit time, we go and check, have we met the rules? And one of two things can happen: yes or no, your transaction needs to be aborted. And so those sort of database academics will notice that this is not a pure optimistic concurrency control scheme, because it's sort of mixed with multi-version concurrency control in that way. But the core right path is optimistic. And so we can go into the trade-offs between optimistic approaches and pessimistic approaches if that would be interesting. But the big thing we get out of this is it minimizes the communication between regions and AZs for these distributed settings.
Yeah, excellent. And there's always trade-offs you're going to make in distributed systems. And, the most popular one is CAP theorem, which is between consistency, availability, and partition tolerance. But really, there's, hundreds of thousands of trade-offs that you'll make when you're actually in the weeds of implementing a service that, especially at this scale, I personally can't imagine. But based on what you're describing, it's certainly very sophisticated. And it's so, coming back to your earlier point about you're relying on Postgres as your main, query engine, let's call it that, which is great because, so many applications are built on Postgres. There's a lot of development happening there, whether it's, building relational database applications there. Now there's some nascent AI-based applications with the PG vector, and, has a great open source community of extensions. And, we had Gwen Shapira from Nile who came on the pod and really dove into all the, just how rich the extension community is too. We really appreciate learning about that. Now, of course, Postgres has its own, logging as well. You spoke about journaling, which is a little higher level, but, Postgres is the database itself, like a single instance, will have its own write-ahead log, and, it'll have its own buffer cache. And it'll have all these components that sort of come in with a database off the shelf. So are you also piggybacking on the logging of Postgres, or is that something you've also built into your own layer of abstraction?
Yeah, so that whole kind of durability storage layer of Postgres, we aren't using, because we wanted to build in this fairly unique set of distributed properties, which isn't Postgres's core concern, right? That it is designed to be durable to storage on a single machine. There's obviously some replication machinery there too, but we needed to replace all of that, both for scale out reasons and for fault tolerance reasons, right? We wanted to be, durable synchronously across multiple AZs or across multiple regions. We wanted to be able to transparently partition data into multiple write partitions and multiple read partitions. And those were things that, that layer of Postgres, as great properties as it offers, doesn't do. And so we replaced those pieces of the engine.
Yeah, wow, that's incredible to hear about. And, certainly a very sophisticated design, and it's a really focus on serverless, but also high availability and scale. which is a truly unique combination. And it makes, the end result to users, it makes it easier and less costly to run databases than ever before. So what would you imagine are some of the new types of use cases this architecture can enable that just weren't practical?
Yeah. Um, well, before I answer that, and that's a great question. I did want to say one of the reasons that we chose Postgres, is that it is this really great extensible modular architecture. It's actually, for its age and complexity, it's a beautifully architected piece of software, um, and so it very naturally allows the kind of deep surgery that we've done on it,
Oh,
and and that's exciting, and I think it's one of the reasons that we Postgres is having this kind of moment across the industry, right? Like it's just super popular right now for good reasons, and one of those reasons is that it provides a huge amount of extensibility and flexibility, and lets folks build all kinds of cool things with it and around it in interesting ways. Jumping to your question about use cases, one of the things, we're really trying to do here is simplify architectures. And so um, if you look at an architecture today based on, a traditional relational database, there are often a lot of blocks, right? You will have your primary database. You'll maybe have some failover databases in multiple data centers. You'll have machinery about managing, detecting failures and managing those failovers. You'll have replication machinery, keeping those replicas in sync. Um, often because you only have a single consistent primary, you'll have a caching layer on top of your database. You'll have some kind of change data capture or replication mechanism keeping that cache up to date, or you'll have logic in your application, keeping that cache up to date. Often you'll have a bunch of plumbing out to infrastructure for doing reporting and analytics. You'll have plumbing to infrastructure for doing backup and restore, point-in-time recovery, audit, and so on. And so these architectures, as you try and take a database into being a reliable whole kind of end-to-end application solution, they become quite complex. And so what we've been trying to do, both with DSQL and kind of across the whole AWS data family, is really simplify that. And so, with DSQL, what we've said is, hey, this is already multi-AZ. You don't need to worry about those multiple replicas. We'll handle that replication and moving of data if they're failures for you. You don't have to worry about caching in the same way. We'll scale out for reads and for your read load. We'll keep your reads local within an AZ or within a region, and optimize that latency for you. You don't need those blocks in your block diagram. Backups are built in, restore built in, right? Like these pieces are built in. And so what we've really tried to do is take all of those use cases that folks have, all of the things that add complexity to architectures, and really simplify them. And I think, if we've succeeded there, I think there's a cool set of applications we're going to unlock, which I'll talk about in a second. But really, it's about simplifying those things. And then, what do we unlock? Well, I think the new architectures is we're hoping that it becomes much easier and much more cost effective to run active architectures.
sure.
Especially in the multi-region setting, folks tend to go to active failover architectures, mostly for operational simplicity reasons, mostly because their database doesn't do active in a nice way. And those architectures can be hard to reason about. They can be hard to make sure they actually work in the days that you need them. They can be more expensive to run. And so, we've really tried to make it as easy as possible to run active. You can have both sides of your application running. They work because they're running all the time. Both are handling customer traffic all the time. You're able to, keep keep that infrastructure paying, on both sides. You don't have infrastructure that's just sitting there gathering cost and no value to your customers. You can send traffic to the region that's closest to it to get better latency. It's a whole bunch of
Oh, wow.
goodness, and we're just trying to make those architectures easier to achieve.
Yeah, that's incredible. So based on what you're saying, you'll have an even higher level API in addition to what Postgres offers out of the box to store and query your data. And you were talking about region locality and things along those lines. So
And those are just built in, right? Like you just
uh,
connect with your Postgres client. You look up the DNS name, you connect from your Postgres client, and all of the locality stuff will be handled. If you're running in EC2, even the kind of AZ and data center locality will be entirely handled by the infrastructure without you having to worry about it at all as an application programmer or as a system operator.
that's absolutely incredible. And uh, developers have worked with Postgres before, and especially optimizing it, you might use, shared buffers or, PG pre-warm to govern, which data stays in your buffer cache. Uh, would those features be abstracted away or also something that like a native Postgres developer is experienced with it be able to access?
Yeah, so I think that's a sort of mixed answer to that. So, a Postgres developer, you'll still need to think about the way that your queries and schema come together into execution plans in the database. You're still going to want to pay attention to that explain and that explain analyze. Like, how much work am I asking the database to do on my behalf? Because anyone who's written, or written a lot of database code or operated database systems knows that the difference between the database doing, O1, O login, or even O n squared data, work for you, it's hard. It's hard to look at a query and actually know, like, how much work is the database going to do? And that's where that explain comes in. Like, hey, what are you going to do when I ask you to run this piece of code? And so that remains just as relevant. The stuff that we don't think is going to be as relevant is that preheating of the cache, is that tuning of buffer and cache sizes and so on. Right? Like we've tried to abstract those away and automate those so the operator doesn't need to worry about them.
Oh,
Right?
wow.
Those
So are they,
certain still exist, but they are not exposed to the operator, to the developer. They're things that are handled in our system.
oh, wow. And just clarify if I can ask from my side, is that with some sort of per tenant caching design?
Yeah, so there is some caching, especially around very frequently accessed tables like the catalog, which is a per tenant isolated caching design. But most of what we've tried to do is avoid the need for aggressive caching at the query processor layer by pushing down work to storage.
Mm.
And so the storage interface is not key value. It's actually quite a rich push down interface where you can push down filters, you can push down projections, you can push down aggregates and those kinds of operations. And what's super valuable about that is it makes the interface between the query processor and storage so much less chatty, right?
Mm.
If you think about the interface that Postgres itself would have to storage, it's very chatty. It's very low level. It's like, hey, get me that B tree page, get me that B tree page, give me that page, right? Whereas, in DSQL, it's a logical interface that is, get me all of the rows matching this predicate. And all of that low level data structure wrangling happens locally on the storage node where it can be done in memory or done locally against fast storage, which, saves a whole lot of back and forth and then allows us to scale out that query processor layer horizontally without the challenge of keeping a large coherent cache. And, cache coherency is a classic computer science problem for a reason, and the reason is that it's really hard to get right, especially in the distributed setting.
Yeah, absolutely. And it's so interesting to hear about the implementation here and the design choices you made. And it's truly remarkable, what this can enable. And we talked about use cases. Like on a completely separate, and this is a tangential point. One of the most popular and revenue generating AI use cases right now is code generation. It's developers can write code super fast, and people are looking ahead and saying, we're going to have AI agents write more code and accelerate that process even more. And one of the things that AI is good at is kind of generating procedural code and logic. One of the things you wouldn't want AI to do is provision a bunch of infrastructure for you. So having a service like this where, you can just have a Postgres API or Postgres interface, but the scaling and high availability and that's all being abstracted away from the developer, whether it's, human or, AI agents, that could be, a future software development approach that we see becoming more popular.
Yeah, I think that's very astute. In a lot of ways, AI and serverless are just really deeply complementary. Um, you know, the ability to have agents or human in the loop code generation, generate code, generate applications that then run against on compute services, against databases, against storage services that handle all of the operations without having to push that complexity onto that AI to solve. I think that's going to be those are going to be hugely complementary technologies. Now, there is also going to be a bunch of AI powered things that run on more sort of classical architectures, and serverless things that are not AI powered, right? Like I think we fill in the whole kind of matrix there of options. But I do think that combination of kind of AI agents and serverless is going to turn out to be a really popular and really productive one for a lot of folks building systems.
Yeah, it's really an exciting time to be a software engineer and a data engineer. I know there's some kind of pop science fiction writing out there that's going to replace all engineers. I mean, I don't know if you go look at OpenAI, they're still hiring a lot of engineers. So yeah, or any AI company, even AWS. Uh, So I think it's certainly very cool to see some of the new, like you said, complementary technology come in, like serverless. It does at least simplify the deployment process for AI, especially if there's a commonly used API that's built on at least foundationally like Postgres, which most LLMs are already trained on, and leveraging open standards. I want to get your thoughts. And, you also mentioned that in terms of use cases, just simplifying architectures is the first one. Is there anything else radical that you see being enabled by DSQL?
Um, yeah, that's a really that's a really interesting question. I don't have anything particularly radical that I can share. Obviously, this is something that we think about super deeply. But maybe one hint that I can drop is I think having this journal at the core of the system, having this commit log at the core of the system, um, enables us to do some really cool things with the kind of history of transactions and so on that is hard to do in classical systems, and I think we'll be able to build some very cool data features around that over time. And then I think having this serverless infrastructure and scalable infrastructure gives us a lot of flexibility in the ways that data is accessed over time, right? And so right now it's Postgres and SQL, but it could be a whole lot more options than that. So very very fun. And to your larger point, right, about the industry, like I think this is honestly one of the most exciting times in the data, and computer industry that certainly that I can remember. Just the last year in the data space has been extremely exciting. There's so many interesting trends and so many cool new technologies coming along that it's just a really, really cool time to be involved with this stuff.
Absolutely. Every day there's new announcements. It seems like we're making these big kind of categorical advancements in technology on a much more frequent basis now since the start of the AI wave. So it's been very fun to follow along with it, and especially I have a distributed systems and data background, so especially the work that you're doing, and I've had a lot of fun following along with your blogs. I just love how generous you are with your insights and the work you're doing, because there have been companies that have built incredible IP and databases that they don't really get into depth of their implementation as much. They will. You have to sort of find. You have to go find it. But the way you just blog about it is really cool, and I definitely recommend the listeners of this podcast, if you haven't yet, to subscribe to Marc, follow him on X, follow him on Blue Sky. I'll let you actually answer. Where can people follow along with?
Yeah, X and Blue Sky are great options. You can follow my blog. I tend to put most of my long form writing there. I've been doing a little bit more on LinkedIn recently, but still not a whole lot there. Although there's a really interesting kind of technical community that seems to be building around that platform. And so any of those four options is great and should keep you up to date on the things that I've been doing. And I really appreciate your comments on my blog. Great to hear that folks enjoy it.
Absolutely. They do, me and my friends who also work in the industry, talk about it. And it's just really interesting to read and see what's going on. It's almost like I want to say, uh, you know, watching a movie and then watching the behind the scenes footage. It's just very captivating and cool to learn about the process and the thought process too.
Yeah, it's really cool. Thank you.
Marc Brooker, thank you
Yeah,
so much for joining this episode of What's New in Data.
yeah. Thank
Thank
you.
you to the listeners for tuning in.
Yeah, really appreciate it. Thank you.